Good. All right. So our next speaker will be Soheil Behnezhad, settling the past complexity of approximating matchings in dynamic graph streams.
Thank you so much. Thanks for inviting me. Today I'm going to talk about the past complexity of the approximate maximum matching problem in dynamic graph streams. And this is a joint work with Seper, Christian, Kiran, and Janani. And Janani should get the credit for the slides. I think she's done an amazing job. Okay, so we're going to talk about matchings in graphs. So the input to the problem is a graph G on vertex set V, edge set E. There will be n vertices in the graph, m edges in the graph. And what we want to find is a matching. And quick reminder, a matching is just a subset of edges such that every vertex in the graph has at most one edge in the matching, right? So this is a matching in the graph. And we typically want a large matching. We want to put as many edges in the matching as possible without violating this constraint. All right. And our goal is to find such a large matching under memory constraints. In particular, we assume that we do not have enough space to store the whole graph, yet we want to find a large matching of it. Okay, so slightly more formally, we'll be dealing with the streaming setting, or more specifically, the dynamic streaming setting. So the vertex set of the graph will be known. We have like n vertices labeled from 1 through n. And the edges of the graph arrive one by one in a stream. So this is going to be the stream. Maybe like the first element in the stream is this edge insertion. Like there's this edge E1 between these two vertices. It's inserted in the graph. Second element could be like another edge insertion, maybe like then another edge insertion. But we could also have potentially like edge deletions. So maybe like the next element would delete edge E1 that was inserted at the beginning. Okay, and what's our goal? Our goal is to, at the end of the stream where the whole graph is defined, we want to report a large matching of this graph. And we assume that the space that we have available to us is proportional to the number of vertices, but it's not enough to store the whole graph, right? So the number of edges in the graph could be like as large as n squared, but the space that we have available is n pi log n. So maybe like we can store like a counter for every vertex, but not all the edges of a vertex. Okay, any questions about the model? Yeah.
So why do you assume this dynamic stream if you solve the problem only at the end? Why don't you assume that you have a graph and you have to solve this problem? What does this dynamic stream contributes to your problem?
Like why do we allow edge deletions? You mean? Like why is it not just like...
Eventually, at the very end of the stream, you have a graph, right?
Yeah.
And you do not solve the problem as updates are taken.
Yeah, that's a good question. You can also like, that's another good question to also like maintain a matching as the edges are inserted and deleted from the graph. That's...
I think the question was more like, you could model this as like a sublinear thing where the edges, like, you can query, is there an edge there?
Yeah, that would be like another model of sublinear time algorithms. Here, the focus of this talk, and so I guess the workshop is on space. Yeah.
We just don't have space to store the graph. Right?
Yeah, we don't have the whole graph.
I see, okay.
Yeah. So think of it as like you have the whole graph written in the hard disk. You can only like read it line by line, and you don't have like enough RAM to store the whole graph. And we want to find a large matching of that graph. Yeah.
Then why there's deletions?
Yeah, so like there are also like natural scenarios where deletions are happening. Like for example, like in social network, people like unfriend each other sometimes. So, yeah. Okay. All right. So yeah, so this is the model, and one thing I wanted to emphasize is that like we are going to talk about multi-pass algorithms, so we allow the algorithm to go over this stream multiple times if needed. Okay, and as we will see, this is going to be necessary. Okay, my focus will be only on constant approximate maximum matchings. So any matching that's let's say like 1,000 times smaller than the maximum matching is fine, so long as it's not smaller than that. Okay, and the reason that I'm going to only talk about constant approximate matchings is that if we find a constant approximate maximum matching, we can just immediately boost the approximation to 1 plus epsilon. Right? So in particular, if we have a constant approximate matching that takes p pass, if there's an algorithm that reports a constant approximate matching in p passes and in space S, we also get automatically an algorithm that returns a 1 plus epsilon approximation in asymptotically the same number of passes and the same space, so long as epsilon is constant. Okay? So all we need is to find a constant approximate matching. So really the question is, if we have this much space and polylog space, and we want to report a constant approximate maximum matching, how many passes do we need over the stream? That's the only parameter that's left to be determined. Okay. Okay. So what was known for this? So already when the model was defined in 2012 by Anguha and McGregor, they realized that an existing algorithm leads to a log n over log n pass algorithm that finds a constant approximate maximum matching. And a few years later, it was shown by these works that one pass is never enough to find a constant approximate matching. So at least we need 2 passes. So based on these 2 results, the answer to the question that I had on the previous slide would be somewhere between 2 passes and all the way to log n over log n. Okay.
How much memory is needed for 1 pass?
I believe you need n squared. Yeah. If I remember correctly. Yeah.
And how does this, if you said maximum, all right? If I want to
The lower bound holds for, both of these hold for constant approximations. So this lower bound holds for even constant approximate matchings.
Is there a notion of an approximate maximal matching?
You mean like a matching that's not a subset of another matching?
Yeah.
Maximal? There is a notion of approximate maximal matching, but that doesn't make the problem any easier, because any maximal matching is also like a constant approximate maximum matching to approximation.
Yeah, okay.
Yeah, so that doesn't actually make the problem easier at all. Okay, so what we do is we first improve the upper bound from log n roughly to log n. So from log n over log n to log n, so it's an exponential improvement over the number of passes. And we also improve the lower bound. We also show that log n passes will be needed for any algorithm. So basically just the complexity of the problem is going to be log n. Okay, so slightly more precisely, we prove these 2 results. The first is an upper bound that there's a log n pass algorithm for constant approximate maximum matching. And again, I want to give a reminder that like the approximation can be just immediately boosted to 1 plus epsilon for any constant epsilon approximation. And on the other hand, we also prove that like with n polylog n space, any constant approximation requires log n passes. Yeah.
Is insertions only very easy?
Insertion only constant approximation is easy. As the edges arrive, you just construct a maximal matching. And you only need order n space because the matching will only have order n edges. But with deletions, that's, yeah. So the lower bound says that you actually need like log n passes.
And when deletion is allowed, you cannot do also just order n. It's not possible. You need at least n polylog n space.
Order n, you mean like n?
Order n space is not possible.
Bits or words?
Yeah, bits.
Or words?
Say words. Yeah. Let's not say.
I'm actually not sure about that. Yeah, we were not too careful about the polylogs in this result. Yeah, that's a good question. Okay, so for the rest of the talk, I'm only going to focus on the upper bound and the things that go into proving that there's a log n pass algorithm. I also want to say that, like, even though I am phrasing this as an algorithm in the streaming setting, it also has implications in other space-restricted models. For example, the MapReduce model or the massively paired computations model. It leads to the first algorithm with near linear memory that runs in log n rounds of MapReduce and uses order n working memory. Previous algorithms required superlinear in n working memory. Okay. All right, so about the techniques, really if I wanted to just give a one sentence summary of what we do is we give a new connection between matchings and maximal independent sets. So quick reminder, what is a maximal independent set? It's an independent set that's maximal. So you want to select a subset of vertices that are not adjacent, and you want to make sure that this subset is not a proper subset of another independent set. Right? So in other words, like you want to just add vertices as much as possible until you cannot add any more vertices with the independent set. OK, so this is a maximal independent set. And finding a maximal independent set is usually really easy. Like in a classical setting, for example, we can do this greedily. Let's say we pick a random, we pick an arbitrary ordering of the vertices. Any ordering works. We go over the vertices one by one. So the first vertex we added to the independent set. And then to preserve independence, we remove its neighbors. The next vertex that's in the ordering, we add it to the independent set again. If it has any remaining neighbors, we remove those. And this gives a maximal independence set at the end. Now, this works for any arbitrary ordering. If we replace the arbitrary ordering with the random ordering, we again get a maximal independence set, but we get a randomized greedy maximal independence set. And it has many, many nice properties. We'll see two of them today. One of them is that a randomized greedy maximal independence set, if this ordering is random, we can actually find it very efficiently in the streaming setting, in dynamic streams. We can find such maximal independence set in just log n passes. For a given ordering, it's going to require like polynomially many passes. It's going to be much harder. But for random orderings, we can do this in log n passes. And I'll get back to this in a few slides. We'll see another property of it, which relates it to matchings. Yeah, trying to manage my time. Yeah, so first I'm going to talk a little bit about fractional matchings and vertex covers, just a quick reminder, nothing new. And then I'll talk about the connection between maximal independence sets and matchings that we proved in our work. OK. So I'm going to go over these a little bit faster, because probably many of you have seen these before. So what's a fractional matching? Instead of picking edges integrally, we just pick them fractionally. So we assign a fractional value between 0 and 1 to every edge, subject to vertex constraints. That around every vertex, some of these values that we pick does not exceed 1. We do not want to pick more than one edge for a vertex. That's all. And if we find such a fractional matching, a maximum fractional matching, we want to maximize some of these fractional values on the edges. If we do find such an object, then we can immediately round it. How do we round it? It's very simple. You just sample every edge independently with property xe, maybe times log n. And then the support, the sampled edges will include a constant approximate maximum, integral maximum matching of the graph. Okay? We will lose some integrality gap, but still it's going to be a constant approximation, and that's all we need. So we are going to try to find a constant approximate fractional matching now. It's also useful to look at the dual of this. It's going to be the fractional vertex cover problem, where we want to assign real values to the vertices between 0 and 1, such that for every edge in the graph, some of the values on the two vertices, two endpoints, is at least 1. This is what a fractional vertex cover is. And these are duals of each other. If you want to minimize the fractional vertex cover, its value is going to be the same as the maximum fractional matching of the graph. OK. So that was just a quick recap of the linear programs for matching and its dual. So what's the connection to MIS? So there's an immediate connection to MIS from the perspective of vertex covers. So if you take a maximal independent set, the complement set of the vertices will always be a vertex cover, right? Why? Because there's no edge between the MIS vertices because of the independence property. So all the edges either go from MIS and its complement or between the vertices in the complement. So they will all be covered by this set. Okay? So this is an immediate connection. The question is, like, is this actually a good vertex cover, or is it much larger? Generally, it can be really large. It's not going to be a good vertex cover generally. So for example, like this is one graph. The minimum vertex cover of this graph is 2. If we select these two vertices, every edge is covered. These red vertices form a maximal independent set. And if you look at the complement, it is a vertex cover, but it's much larger than the minimum vertex cover. It has 5 vertices. Okay? So generally, just finding a maximal independent set and taking the complement is not going to give us a good vertex cover. In fact, it could be just n times larger than the actual minimum vertex cover of the graph. But here's the second nice property of randomized greedy MIS. Valt proved not long ago that if you find a randomized greedy maximal independent set, its complement is actually going to be a 2 approximate minimum vertex cover. So it's going to be an expectation 2 times larger at most than the minimum vertex cover of the graph. Okay? Very different from arbitrary maximum independence sets. Okay, so this is useful. Why? Because we know how to construct randomized greedy maximum independence set in the dynamic setting, and then we can take the complement. It's going to be giving us minimum vertex, 2 approximate minimum vertex cover. Okay. So this was the algorithm for finding a randomized greedy maximum independence set, and we can also view it as an algorithm that constructs a minimum vertex cover, an approximate minimum vertex cover of the graph. How? We basically pick a random ordering over the vertices. We go over the vertices one by one. Every time we add a vertex to the maximum independence set, we look at its neighbors that are still in the graph, add them to the vertex cover. These are going to be the ones removed by that vertex. And this is going to be giving us a 2 approximate minimum vertex cover. Okay. So what's left is to go from this 2 approximate minimum vertex cover to a matching. Okay. So that's going to be our contribution. All right.
I guess.
Yeah.
I thought you were going to say one of the things that gets to next is the stream is presented to you. You don't get a random ordering of it. You don't get to pick the ordering of the vertices.
Yeah. So the stream is over the edges. The vertices are, we have access to the vertices. We have enough space to look at all the vertices and maybe like, randomly permute them.
Okay. Sorry.
Good. Yeah, so the proof of Welt's theorem is acute application of LP duality, a primal dual analysis. I'm going to run out of time soon, so I'm just going to quickly say a few words about this analysis. So the analysis works like this. So every time that a vertex is added to the independence set, to the maximum independence set, it looks at the edges of this vertex, these 2 edges, to the remaining vertices in the graph. And let's say like marks these edges. So every time a vertex is added to the independence set, it looks at all of its edges to the remaining vertices. It's going to be a star, and like puts this star aside. So at the end of this process, we are going to have like a collection of stars. Okay? And this depends on the run of the algorithm. This depends on the random permutation of the vertices. Maybe like after one run, this collection of stars could look like this. Maybe on another run could look something like this. And then it's going to be giving a distribution over these collection of stars. Okay? And what Welt proved was that if you look at this distribution, if you define this probability that an edge is part of this output, then it's going to be a fractional matching of the graph. And that's basically how the proof works. P is just a probability that an edge is part of this collection of stars that I define how we. It's not necessarily 1 degree. It depends on how the algorithm evolves. Yeah. Because the degrees change over time. Okay. Yeah, so the problem really is if we knew what this fractional matching looks like, if we had these probabilities, we could just round it and find a maximal or a constant approximate maximum matching of the graph too. Unfortunately, we don't have this probability. We do not have these probabilities. We cannot compute, even though we know how to compute a maximal independence set of the graph, we do not know how to compute these probabilities efficiently. Particularly, just one example clarifies this a lot. So suppose that the graph is a complete graph. Okay. With one run of the algorithm, the randomized greedy maximal independence set would pick just one vertex, put it in the independence set, and select all of its edges. So every run just selects a star in the graph. And really, we have to just like run it n times and take the average for this to be a fractional matching of the graph. Otherwise, it's far from a matching. It's really huge stars. Okay, if you take this n times an average, it's going to be a fractional matching of the graph. But we cannot afford to do this n times because we don't have memory for that. All right, so I'm just going to quickly say how we construct the matching, which with just one run of the algorithm can construct the matching instead of running it n times and then taking average. So this is what we do. We select a random vertex to put it in the independence set. And then these vertices will be added to the vertex cover. Okay, so these are the vertices that are removed by this vertex. And we look at each one of these vertices and write a fractional value on their edges. So instead of selecting these 2 edges, as with Welt's proof, we look at these vertices, and each one of these vertices sends a fractional value of 1 uniformly along its edges. So this vertex has just one edge, so it just writes 1 on this edge. This vertex has 4 edges, so it writes 1/4 on each one of them. OK, and then these vertices are removed. Next vertex to be added to the independent set is this one. It removes only this one. And this has 3 remaining neighbors, and writes 1/3 on each. This is how we eventually construct a fractional assignment on the edges. Now, it's not necessarily going to be a fractional matching of the graph. If you look at, for example, this vertex, what we write around it is larger than 1. And in general, it's going to be potentially like very far from a matching, fractional matching. For some vertices, if they're unlucky, the value around them will be really large. But what we prove really in this work is that like in expectation, things are fine. And the probability that we write a very large value around the vertex is going to be very small. Yeah, so I don't think I'd be able to say much more about the analysis here, unfortunately. Yeah, so really just like what we prove is that in an iteration, if we expect to write a large amount around a vertex, there's also a large probability that we remove that vertex immediately. Once you prove this, then you can do a probabilistic analysis and show that, like, in fact, like what we construct at the end is very close to fractional matching. OK, I'm going to skip these, the proof of why this is the case, and just finish with a few concluding remarks. So we gave a reduction from randomized greedy MIS to constant approximate maximum matchings. There are a lot of settings when MIS is easier to compute. So for example, MPC and dynamic streams were too. So this led to improved bounds in these 2 models. And we also know that like a constant approximate matching can be boosted to a 1 plus epsilon approximate matching. So we can also get a 1 plus epsilon approximate matching. And I want to also mention 2 open problems. One is what's the right dependence on epsilon? So the n dependency is going to be log n. But if we want a 1 plus epsilon approximate matching, what is exactly the dependence on epsilon in the number of passes? So what we know is that it's going to be polynomial in 1/epsilon. There are lower bounds and upper bounds that the dependence should be poly 1/. I guess the lower bound is log 1/epsilon, but the upper bound is poly 1/epsilon. Figuring out the right bound is open. Another open question is, this is tight for the streaming setting. We have a matching lower bound of log n for the streaming setting. For the map reduced setting, we do not have a lower bound. Not even a conditional lower bound. So technically, for the map reduced setting, one might be able to come up with a constant round algorithm. Ruling that out would be very interesting. Yeah, I guess that's all I wanted to talk about. Thank you.
So can you give us intuition where the log n passes fits into all this?
Like where log n is coming from?
Yeah. Because what you said, I didn't see a log n.
Yeah, so really the log n comes from, so we use the existing maximum independence set algorithm and show that like if you have that maximum independence set, then you can turn it into to matching. And that maximum independence set algorithm runs in log n many rounds. But if you want intuition of why that takes log n rounds, basically after every round, you shave off the maximum, roughly speaking, the maximum degree of the graph polynomially. So let's say it goes from n to root n, and then from root n to n to the 1/4. And after log n passes, you're done, right, basically. Yeah?
Sorry, I didn't catch what you said. You repeat what you said here?
Like,
Why is log n?
so like you shave off the maximum degree after every pass polynomially. So it starts.
By shaving off, you mean you can eliminate edges that you know won't be.
You will add some vertices to the independence set. You remove them and remove their neighbors, and in the remaining graph, the maximum degree will be bounded. So the maximum degree drops from n to, let's say, root n, and then from root n to n to the 1/4. And if you do this log n many times, you're done.
So just, do people have like log n lower bounds in MPC for anything? I mean, does the technology exist for that?
So this is all in MPC with linear in the number of vertices space per machine. In that setting, we do not even have the conditional lower bounds.
But I guess, does anybody know how to prove a lower bound in MPC? Like,
Unconditional, no. Yeah, unconditional, if you prove any lower bound, it would imply major circuit complexity lower bounds that are out of reach, it seems. So no, but there are some conditional lower bounds. We don't even have a conditional lower bound for this range of parameter.
So
Yeah.
actually on that note, so the lower bound is for MIS,
The lower bound is for matching. No,
not for matching. I see.
it is for matching.
No, but is it also, because you have a reduction to MIS, so it also applies to MIS?
No, the proof for the lower bound is not through a reduction to MIS.
No, but if you can do MIS faster, I thought you can do matching also better, no?
Yes. But one could maybe come up with an algorithm for matching that doesn't necessarily use MIS. We also ruled that out. So we proved that any matching algorithm needs log-log passes.
Maybe I'll ask another quick one. So I'm still trying to get an intuition for how did deletions make things challenging? Like in the
Oh yeah. So the algorithm is very simple if you don't have.
yeah, no, I understood that part, but like in the actual algorithm you showed us,
Right.
which part of it is used to handle deletions?
Oh, so really the algorithm, yeah, so there's going to be implementation details that I did not talk about. But really the way that the algorithm works is that you select a subset of vertices and you really look at what happens internally between those vertices at the end of the stream, and you will have enough space to store all of the edges between them if the set is sparse enough and the number of the vertices in the set is small enough. And then you can just store everything. So as things are inserted and deleted, it's fine. You only look at the edges at the end of the stream, what remains in the subset. So it's robust to deletions, basically.
all right, thanks.